All right, we are going to go over the kinematic graphs. So we're going to discuss how we find things on each of the 3 kinematic graphs. I'm going to make a list over here of the types of things we could find. So we could find position, we could find distance, we could find displacement, we could find direction of travel, we could find speed, velocity, we could determine if something is speeding up or slowing down. We could find acceleration. Those are the main things we're going to be looking for. Okay, so keep those in mind and notice which of those we can find with each type of graph. So the first one we're going to do is a position. That's a terrible marker. Is a position time graph. So this would be a position time graph. I'm going to do a straight one to begin with. So this is my first example. Okay, so this is my position time graph, and I'm going to see what I can find over on this list of things. So first off, I can definitely find position. So position would just be the y value at a given time. So let's try an example. I'm going to say that this is 1 second, this is 3 seconds, and this is 4 seconds. Probably not to scale. This will be 5 meters. This will be -8 meters. Making up numbers. So my first example would be, what is the position? At 4 seconds. Well, I'm located right here, so my y value is somewhere around here. Let's call it 2.5 meters. You'll notice this is a positive number. If I have a positive number, I am assuming location is positive. I'm not guessing. I don't know, is it positive or is it not? If I write a positive number, I'm assuming I have a positive location. Another example, what is the position at 2 seconds? So I'm going to assume 2 seconds is right about here. My y value at that location is -8 meters. So my position would be -8 meters. I could write that as x equals, my current position is equal to -8 meters. I know it's an x. I have a little bit of information here. I know it's an x, so it must be moving in a horizontal direction. So I can write x equals -8 meters. If this just said position instead of x, I wouldn't know exactly whether it was horizontal or vertical position. I'd have to guess, which I'm not going to do. So I'm just going to say the position is 8 meters in a negative direction from the start. Don't know which negative direction that is, but 8 meters from a negative direction from the start. But ours does say x. All right, that's position. That's pretty easy. Let's talk about distance. So distance, I have to count how far the object has gone. I'm not looking at a specific part of the graph. I am actually counting how far has my graph line traveled across the graph. So, for example, after 4 seconds, how far has the object gone? So that's the question. So if I'm looking for distance after 4 seconds, well, I started out at 5 meters, and I have traveled from 5 to 0, so that's 5. That got me here. Then I've traveled another -8 meters, but that's 8 meters because distance is scalar, so it's just a positive value. I traveled another 8 meters from 0 to -8. Then going back, I traveled another, well, we'll start here, 8 meters to get back to 0 at 3 seconds. And then I traveled another 2.5 to get up to here. From about 3.1 seconds until 4 seconds, I'm at the same position the whole time, which means I'm not moving, so my distance is staying the same. So if I add this up, 23.5 meters would be my distance. So this is not like I look at the graph and, okay, it's above the x-axis, I can figure it out. No, I actually have to go and say, where did I travel? I don't care how long it took me to get there. Don't care when I went. Don't care which direction I was going. How far did I go? So I went from 5 to 0, that was 5. From 0 to 8, that's 8. From 8 to 0, another 8. From 0 to 2.5, my total, 23.5. All right, what about displacement? Displacement is how far my current y value is from my original. That means t equals 0 with an asterisk, y value. Another way you can think of this as is position final minus position initial, because that's the equation for displacement. So if you don't want to think of, oh, displacement's finding something new, then follow what you already did for position, right? That's just what is the y value at a certain time. Find the y value at your initial time, x naught, and your final time, x, and subtract them. So let's do it that way. What is the displacement after the first 3 seconds? So my initial position at 0 seconds is at 5. So my initial position is 5. My final position is at 0 at 3 seconds. So my displacement is 3 minus, sorry, I put 3. I meant 0. So sorry. Is 0 minus 5. So I've been displaced -5 meters. Okay? Now, I put an asterisk right here. It says, how far is my current y value from my original t equals 0? My original might be t equals 0 if it asks this question the first 3 seconds, or after 5 seconds, or from t equals 0 to t equals 2. But what if it asks between t equals 1 and t equals 3? So what is my displacement now between t equals 1 and t equals 3? Well, I do the same thing. My x initial, that's at 1 second now. I'm located at 0 meters. My x final, I'm also located at 0 meters. So my delta x, x minus x naught, equals 0 minus 0. My displacement is 0 meters. So that's how I would find displacement on a position versus time graph. What about direction of travel? Well, this is the direction of my velocity. So remember, velocity is a vector component. Velocity is a vector component. So it's made up of two pieces, the speed and the direction. So when I ask what direction am I going, that's the direction I'm traveling. That's the direction of my velocity. So we're going to get to this in a second when we cover velocity. But the velocity of a position time graph is the slope of a position time graph. So I'm going to be looking for the direction of my slope. Of the slope. I'll put, it's not mine. I don't want to be possessive here, of the slope. So if we do an example, at 2 seconds, what is the direction of travel? Well, at 2 seconds, oh, I picked a bad time. Let me make that 3 seconds. It's changing directions at 2 seconds. Ignore that. At 3 seconds, my slope is positive, right? I have a positive slope. I'm increasing. I have a positive slope. So that means I'm going to be traveling in a positive direction. So my slope is positive, so I'm traveling in a positive direction. Notice, okay, my direction does not change when I cross the x-axis. It is my slope and my slope only. So I don't care that I crossed the positive x-axis. All that tells me is now I'm located at a positive position instead of a negative position. That's what crossing the x-axis means. But I'm still traveling in a positive direction as long as my slope is positive. So this would be a negative direction until 2 seconds, a positive direction until 3.2, and then no direction because I'm not moving, right, for the remaining part there. Next up on my list is speed. So speed, again, is the magnitude of velocity. So it would be the magnitude of the slope. Again, velocity is made of two components. It's a vector quantity. So it has a direction, which way am I going, and an amount. That's the magnitude part. How fast am I going in that direction? So direction of travel was which way. Speed is how much. So to do this, if I want to know what is my average speed between 2 and 4 seconds. Okay, well, I just want to know what my slope is between 2 and 4 seconds, right? I could just calculate it. So from 2 to 3.2 seconds, it's something. Oh no, my slope changes from 3.2 seconds to 4 from what it was from 2 seconds to 3. That's a problem. So I can't actually just find the slope. So that was an option. That's number one. What I'm actually going to have to do would be displacement over time. Specifically, actually, this is speed, so distance over time. S equals D over T. So between 2 and 4 seconds, I traveled 8 meters plus 2.5, so I have a distance of 10.5 meters in a time of 2 seconds. 2 to 4 is 2 seconds. So my speed would be 10.5 divided by 2, which is 5.25 meters per second. So in this case, even though velocity is slope, since the slope changed, I couldn't use just the slope to find my answer. So I would use average speed. Speed is equal to distance over time to find it. Let's do another example and see if we can't use slope this time. So let's go from 1 to 2 seconds. So this is it from 1 to 2. So I want to know my slope for this section right here. So I have a rise, I went down 8, over a run of 1 second. So I get negative 8 meters per second is my slope, and therefore, is that my speed? No, you're right. Speed is distance, so it would just be positive 8 meters per second. I don't care which way I'm going, I care how fast I'm going. So this is how I could do it. What if I wanted to know what is my speed, not between two timestamps, what is my speed at 1.5 seconds? So this is called instantaneous speed. It's not an average, which is defined as distance divided by time. It's how fast am I going this instant. And here's the trick. If you have to calculate it, it's not an instantaneous speed. You have to know it. On a graph, you have to know it. So if I know the slope between 5 and negative 8 here, between 0 and 2 seconds, I know that whole slope is negative 8. The speed is 8, right? But I know that for the entire thing because the slope is the same the entire time. The entire time, it's always 8. So if asked, what is it at 1.5, I know it. I don't have to calculate it. I don't have to do an additional calculation. I know that the entire time from 0 to 2 seconds, it's 8. So the instantaneous speed at 1.5 seconds is also 8. So I'm going to make a note over here. This will apply to velocity as well. Average speed is distance over time. Instantaneous, I need a constant slope. If I have a constant slope, then I know what the slope was the whole time. So at every second along the way, I know what it was. Awesome. All right. That leads us to velocity. Velocity is the slope of a position time graph, right? Because velocity is change in position over time, really change in time. But we just write time because we do. So that would be a change in y over a change in x. So slope is velocity. So if I want to do the whole thing, right? Example, velocity, average, from 2 to 3 seconds, let's say, right? In this case, I can do it a couple of ways. I can calculate the slope. I can say, okay, well, my rise was 8, my run was 1, so 8 over 1, I get 8 meters per second, right? Just like I did with speed, I can use the magnitude of the slope, except this time it's the whole thing. If it had been negative, I would have left the negative in there. Or, since it's average, I can still do V as displacement over time. My displacement is 8, x initial, x final. So this is 0 minus 8 minus a negative 8, which is 8. So that's how I got that. Over 1 second, so I again get 8 meters per second. If I want the instantaneous velocity at 2.5 seconds, it would be 8 meters per second. Again, didn't have to calculate it. I need constant slope so that I know that whole time from 2 to 3 seconds, I have a slope of 8 meters per second. That whole time, I was going a constant velocity of 8 meters per second. So if between 2 and 3, the whole time I'm going 8 meters per second, then at 2.5, I must be going 8 meters per second. This is the only way to find instantaneous speed or velocity. When we switch to a velocity time graph, we can do it with acceleration as well. You have to have constant slope on this graph to find it. Okay? All right. What about speeding up or slowing down? So this is when my slope changes, right? My slope is velocity. So if I want to speed up or slow down, that would be a change in my speed, which is the magnitude of velocity. So it'd be a change in my velocity, right? That means I'm going to need to have a change in my slope, right? Velocity is slope. So if my slope changes, my speed's changed. Therefore, I'm speeding up or slowing down. So that would look like, for speeding up, going from a flat slope to a steep slope. And for slow down, that would look like going from a steep to a flat. Let's check it out on our graph. Nope, none. It's a constant slope graph. I drew it that way to make our lives easier in the beginning here, right? This is a constant slope the whole time, so the only place that changes is instantaneously right here, which does us no good. That doesn't actually happen in the real world outside this classroom. There's no instantaneous acceleration, just on these nice pretty graphs that we magically created. So that's not real. That acceleration didn't actually happen like that, nor did that. So we can't say on this graph that there was any change in velocity because it didn't happen over time. It did happen, but like that, instantaneous, right? So this isn't real, so I wouldn't say that it's sped up or slowed down, right? What I'm looking for this is a curved graph. We'll see one in a second. Don't worry. I know you want to see one. We'll get there. That brings up the last thing, acceleration. Acceleration is a change in velocity over time. So again, on this graph where it happened instantaneously, there would be no change in acceleration. Okay? So we're going to save this for a second because on a linear graph, linear position graph, there is no acceleration. Technically, that's wrong. Technically, yes, the velocity changed. But acceleration is a change in velocity over time. And we cheated. We have instantaneous acceleration. The velocity changed, but not over an amount of time. It changed instantaneously, not over a second, a millisecond, a nanosecond, like that. Not possible outside this classroom. Just possible on this graph. So know that. So on a linear position graph, there's no acceleration. But let's see a curved one, shall we? I know you've been waiting for it the whole time. So let's see a curved there we go. So going back to speeding up and slowing down, we didn't have that on the last graph because it wasn't curved. We're looking for a curved graph because we need our slope to change. That is a curve, right? In this case, it's going from steep to flat. Oh, make it flat right there. Steep to flat. So steep to flat, this would be slowing down. Right? So as an example from last time, this would be slowing down because I'm going from steep to flat. So when we go to find acceleration, we need two things. We need velocity, whether it's positive or negative. And then we need that speed up or slow down. We have to combine both of those to find acceleration. If it's speeding up, then that means that my acceleration is in the same direction as velocity. So if I have positive velocity, I would have positive acceleration. Negative velocity, negative acceleration. Cool. If I'm slowing down, acceleration is in the opposite direction as velocity. here's the deal, okay? As a reminder, acceleration and speeding up and slowing down are in no way the same thing. Let's get that out of our heads right now. Speeding up and slowing down are a scalar quantity, and acceleration and velocity are vector quantities. So they're not exactly the same thing. Case in point, if I have positive velocity, let's say I'll do it right here. I have a positive velocity of 10 meters per second, and I experience an acceleration of -2 meters per second. I'm automatically, per second squared, over 1 second, I'm going to have my new speed 8 meters per second. So I slowed down. I had positive velocity, negative acceleration. Positive velocity, negative acceleration, so I slowed down. It makes exact sense. Watch what I do right now. If I had negative velocity and negative acceleration, now I've sped up. I went from 10 to 12. So acceleration, just because it's negative does not mean you're slowing down. Just because it's positive does not mean you're speeding up. You really have to be careful with it. It's two components. It's what is my velocity and am I speeding up or slowing down? If I'm speeding up, acceleration goes in the same direction, right? Just like this. I'm speeding up because I went from -10 to -12, right? So I had negative acceleration to make that happen. If I'm slowing down, I have opposite. So, since this is slowing down with negative velocity, I know that because my slope, hey look, is negative. Wow. So I'm slowing down with negative velocity. That means my acceleration is positive. Let's do one more example to make sure we've got it. What about this one? Pause the video, see if you can figure it out. Am I speeding up or slowing down? Well, I'm flat to steep, so that must mean I'm speeding up. Cool. All right, what about my velocity? Is it positive or negative? Well, my slope is positive, so I have positive velocity. Those together give me positive acceleration. Because if I'm speeding up, acceleration is in the same direction as velocity. So positive velocity makes positive acceleration. All right, that was the position time graph. I'm going to switch over and do a velocity time graph next.